Okay, this example is another example of a banked curve, but this time there is friction helping to keep the car going around a banked curve in a circle. So we know that the circle is going to be going around this way, and force centripetal is the net resulting force pointing inwards. But what do we have now that there's friction? Well, let's do the usual. We have force gravity pointing downwards, as always. And then we have force normal perpendicular to the curve, or to the bank. And this time we're not going to tilt the axis. It's going to be easier for us to keep the x and y's as normal relative to the horizontal. So what do we have then? Well, the car wants to kind of slide up the hill, or up the incline. So therefore, friction's opposing it. So our force of friction is actually located pointing down the incline. We have angle theta here. Therefore, angle theta is right here as well. I'm just going to put a little angle line there, and angle theta is also located here. So now we referenced everything appropriately. So what are our vector labels then? Well, this is force normal. Then this is going to be force normal y. And notice that's going to be found by cosine theta. And the one pointing this direction is going to be force normal x. And force normal x is helping this to stay in a circle, or helping it to do force centripetal. Now what about force friction? Well, here's our vector pointing downwards, and here's our angle here. So this is going to then be force of friction x, and this is going to be force of friction in the y direction. Okay, let's quickly remind ourselves what our trig is for all this. So we have cosine for force normal y, sine for force normal x. This side is touching the angle, therefore force friction x will be cosine. And this one down here, force friction y, is actually going to be sine, because that's opposite the angle. So on inclines, you never know what you're going to get. You might need to change your sines and cosines for x's and y's, as we talked about before. We're going to do the sum of forces in the x and y directions in order to solve this question. So here goes. So sum of the forces in the x direction is actually going to be a net force equal to force centripetal, because the car is going to be going around in a circle. Well, let's take a look at what forces we have going in the x direction. Well, we have force friction x and force normal x. So I'm going to say the centripetal force is a vector addition of force normal x plus force friction x. And I'm going to keep all that positive. We'll call this direction positive this time, just so that I don't have to write 3 negatives and cancel all those out. Well, let's go ahead and solve it. Force centripetal is mv squared divided by r. That's going to equal, now force normal x, that's the opposite side of our triangle here. So that's going to be force normal sine theta. Okay, plus, now we need force friction x, which is this vector here. So I'm going to say force normal mu, which is always what friction force equals. And I'll multiply that by cosine theta. Okay, so that's the setup for the x direction equation. Now let's look at the y direction. Well, of course I have a force gravity going downwards. I have a force normal y going upwards, and a force friction y going downwards. Now I know that'll all add out to be 0, because I can't imagine the car just simply sliding upwards, or going upwards, or flying upwards, or going downwards. So all of those forces must be balanced out. So then I'm going to say 0 is equal to force normal y minus force gravity minus force friction y. All right, so let's go ahead and put all of these vectors as values again. So I'm going to have, I'll start writing here, 0 equals force normal y. Well, let's take a look at that one again. That looks to me it's going to be force normal times cosine of theta minus mg, which is gravity, minus friction in the y. So I know friction is always force normal times mu. Okay, but that's looking downwards here. That's the opposite, so that's then going to be sine of theta. So we're doing pretty well. Just now we've got two expressions and some algebra to solve here. And what's our ultimate question? Why don't we say, let's find the velocity that this car can go given an angle and given a coefficient of static friction. And let's go ahead and record little s's right now. This is going to be a static friction. So I'm going to put a little mu s for each of those. So let's go ahead and solve this. Okay, so let's move maybe mg to the other side and keep everything else there. So I've got mg is equal to force normal cosine of theta minus force normal mu s times the sine of theta. And then I've got mg is equal to, let's factor force normal out. So force normal, and that's going to be multiplied by cosine of theta minus mu s sine theta. Okay, and that will do it for the moment. Let's pause this video and then pick up afterwards in the second video where we can finish solving this out and then maybe add a little concept to that. Okay.